Thank you. Okay, good afternoon, everyone. So, could you hear me from Japan? Am I clear? Yes? No? Okay, that's fine. If you have any question, please raise your hand to instruct me. Okay, anytime. So, first of all, welcome to Taiwan. And we would like to have the universal students to discuss the universal problems in scientific research. So my name is Hongzhang Chen. Okay, I'm an associate professor in Institute of Food Science and Technology in NTU. So I major in the food science, and my specialty is including the food analysis. So today's topic is the applications of mass spectrometry for food analysis. So for this topic, there are two terms identified. First, so the first term is mass spectrometry, aka MS. MS is a powerful technique for molecular identification and widely used in many scientific research such as metabolomics, proteomics, and even microbiota. And then I will try to briefly share some cases about the application of MS on the food science. So this course may not focus on the traditional food analysis, which means the proximate analysis. Okay, so in this course, the food analysis is not to determine the major component of food, but we talking about the molecular compounds. Okay. 他们还没有。不，就是这里要视频。Okay. Sorry. 好 ，Sorry. No. Anytime. All right, you're good to go. Okay. So it's clear? Okay. Okay. So let me introduce myself first. So I got my PhD degree in food science and technology from National Taiwan University in 2010. I started to contact the MS technology since 2009 for establishing the quality control platform for food. During my postdoc career, the Q-TOF performed to evaluate the pharmaceutical effects of the traditional Chinese medicine by proteomics approach. Linear ion trap was utilized to identify and quantify the second metabolites of traditional Chinese medicine by metabolomics study. Nowadays, the foodomic study was performed by OB trap. So I just mentioned there are three types of MS machine. One is Q-TOF, another is linear ion trap, and final is OB trap. So I will briefly discuss this machine later, okay? So why MS is so famous today, especially in food science and in Taiwan? In fact, MS is used for the physics and chemistry area to investigate the ion motion, okay? They just want to talk about the ion physics and ion chemistry for the fundamental research. But why the MS technology is so famous in today? That's because in Taiwan, we pay more attention on MS technology because of the food scandal. It's very important that the food scandal is not equal to the food safety. Okay? Of course, those food scandals may remind us to focus on the quality of the food, especially the contaminated. Okay? But not means that the food will kill you. Okay? That's different. So in Taiwan, in fact, in the worldwide, the food scandal is worldwide. Okay? But in Taiwan, the famous food scandal is in 2011. In this case, is the plasticized in clouting agent. That's because for drink, okay? For drink, just like this is water, right? You can see the water is orbital. But if you want to buy a sport drink, but you buy orbital water. You don't satisfy, right? So you want the water is not orbital, it's cloudy. Cloudy water means the sport drink. Okay, so how to make it cloudy? In food technology, we use the emulsifier to make the cloudy. But in that case, they use the illegal chemistry, so-called pesticides, to making the cloudy. So it's a big food scandal. Okay, but nowadays, there is no any regulation on the pesticides in food because we born in a highly processed area. So all of the material has the pesticides, even in water. So it's very difficult. But in that year, they're using a machine called LC-MS to detect the contaminant. So-called DHP is a pesticide. So after that, many people want to know how could we use the LC-MS to detect the trace amount of contaminated in food. Okay, so in 2013, another food fraud is called Oliver food fraud has gone viral in news, and again, LC-MS play a role to detect the Cooper chlorophyll. This one. So for the natural olive oil, it's not refining. Okay, they just use the cold pressure to make the extra virgin. So like the olive oil. So the olive oil will present as a green color. But in that year, the industry used a current, so-called Cooper chlorophyll, to add it into the non-olive oil to mimic this oil is extra virgin. So it's a food fraud. Okay. So what is a Cooper chlorophyll? It's just like a chlorophyll, but natural chlorophyll will collect it with the magnesium. It's easy to decrease, and the color of the green will easy to disappear over into the brown color. So they use the Cooper instead of the magnesium to make the Cooper chlorophyll to make the oil green. Again, they use LC-MS to detect the contaminated, so-called Cooper chlorophyll. And in 2013, again, they has a food fraud called chemical starch. So I believe that you live in Taiwan, you will eat many types of the food, especially this one. Okay, this one is just like bubble. Okay, but it's made by taro. How to make the bubble is so-called cute, or so-called nice taste. In fact, the starch will retrogradation. Retrogradation is a very scientific term. Okay. Anyways, starch. When starch keep in the room temperature for a long time or keep the low temperature, it will become a stone, right? Okay. So how to prevent this phenomenon? We can use the physical modified starch. Okay. But in that case, they use the chemical modified starch. So they added the methyl anhydride. And also again, we can detect by LC-MS. So after that, you can see that many food scandal in Taiwan. We can use the LC-MS to detect a contaminated, to prevent or to demonstrate that there is a food scandal issue. Even in organic rice. In organic rice, in that case, we focus on the metal so-called arsenic. in fact, we worry about the inorganic arsenic. It's toxic, okay? But we also can use LC, ICP MS to detect that. Whatever, you can see many MS this term to detect the food contaminated, right? But let me emphasize this one. This one is 2014 in Taiwan. They have a cotton oil, so-called refined oil case. But until now, there has no any contaminated will be detected by any technology, even LCMS, GCMS, or MSMS, or high-resolution MS. So I just want to point that the MS technology is not to prevent the food safety. It just focuses on the contaminated, which may remind us we need to focus on that. So if we want to use a single technique to prevent the food safety, it's not the truth, okay? For food safety issue, there are 7 basic principles pointed by the BFR. BFR means the Federal Ministry of Food and Agriculture in Germany. Okay, it's a BFR. So including cooperative responsibility, traceability, official food control, the precautionary principle, independent scientific risk assessment, separated of risk assessment and risk management, and the transparent risk communication. So they have 7 principles, okay? So, of course, the most important principle is this one. This one is cooperative responsibility, which means the HACCP, HACCP, or the FSSC 22000, okay? So in these 7 principles, of course, MS technology could give some information in traceability, official food control, the precautionary principle, and independent scientific risk assessment. Okay, for the traceability, the MS technology could be a traceability technique to trace the material is come from where, such as come from different culture or come from nature or synthetic. Okay, the MS technology could do that. And this one is official food control. That's based on the legislation. Okay, for food, they have their own compound profile, and the MS could detect this compound profile. In addition, some of the regulation drug, such as pesticide, may be used for agricultural material. They also can be detected by LC, MSMS, and GCMS. Okay, so of course it's useful. And the precautionary principle is very, very important to prevent food scandal. However, they need a novel technology, so-called non-target analysis, to detect the contaminated but not traditional way. Okay, so of course HRMS could do that. Okay, the high-resolution MS technology could do that. And this one is independent scientific risk assessment. For the risk assessment, we need to know the exposure, of course, the level or the amount of the contaminated in food or in our body. Okay, so we have the exposure data, then we can calculate the risk assessment. So based on these 7 principles, basic principles, MS technology, of course, is useful in food science, okay, but not all. Therefore, we know that the MS should not be a panacea for food safety. MS plays just like a detector to looking for something wrong, okay? Because MS has a powerful quantitative activity to measure the amount of the target market, such as adulteration, illegal chemical, pesticide residue, contaminated, or the quality marker. Okay, it's very important that the target marker. Okay, I mention this work because target is very important. So many scientists say that we can use the MS to detect the unknown compound. I'm sorry, for the unknown compound in chemistry, the MMR is the only way to do the compound structural elucidation, but not MS. So MS is to detect the known compound, but not unknown. Okay. Let's review the evolution of the food analysis. Okay. For food analysis, the basic composition including the moisture, protein, carbohydrate, and ash, and lipid. Okay. They were detected by a simple chemical reaction, just like the Kyoto. The Kyoto is for the nitrogen determination for protein. Okay, and then the first electronic portable pH meter was used to detect the maturation of lemon. So if the lemon is maturated, the acidity will increase. So we can use the pH meter to detect that. Okay. And in 1914, the electronic spectroscopy were used for more detailed analysis, such as UV, IR, and MMR. So the evolution of chromatography method is needed to support this spectroscopy method. So since the 19th century, by Ziwei, they have a critical role in development of chromatographic method, such as GC and LC. So GC is aka the gas chromatography, and the LC is liquid chromatography. Of course, the HPLC is high performance liquid chromatography. Okay, so many techniques will evolution right here. In addition, the MS technology was raised in 1922 by Aston. So the Antwerp won the Nobel Prize in 1999. And in 2002, the ESI and Maldi won the Nobel Chemical Prize because the complex matrix could be detected to gain the higher efficiency on MS technology. So the rise of the modern analytic platform gives us the RMX study. Therefore, we combine this technology to do the RMX study. In food science, they call it foodomics. I'm not sure this term is right or not. That's because if we remind that, the genomics means there has a genome. So we have a genomics to detect all of the genome. For proteomics, they have proteome, right? So we detect all of the proteome, which means the proteomics. Again, the metabolomics is to detect all of the metabolites, right? But what is foodomics? Does there has a foodom, or there has any chemical profile of food could be detected? So they call foodomics. I'm not sure. Okay, but this term is arise for everywhere. So just remind that since 2011, the Italian food scientists point out the term of foodomics. So they said, what is foodomics? Foodomics is a discipline that studies the food and nutrition domain through the application of the RMX technologies. So we know that foodomics is a term, but they don't have the foodom, okay? They just use the other RMX technology, including genomics, metabolomics, proteomics, and so on, to evaluate the food issue. So they call it foodomics. So as shown in this graph, there's a global perspective of the knowledge of food. So the aims of foodomics are the assessment of the olfactory sensing and the biofunctionality by the olfactory sensing and the food functionality, right? And according to the different approach, the different technique may be used. Okay, so such as for MMR, they can use to the metabolomics to detect the taste and olfactory sensing. Of course, if you want to do the nutrient genomics, they use the PCR to do the genomics, okay? But we can see that the mass spectrometry is a powerful technique to detect the proteomics, peptidomics, metabolomics, and even the lipidomics, glycomics, any omics, okay? So in my lab, we just want to use the MS technique to carry out the food authenticity. But you can see that for food authenticity, the traditional way is to use the genome. They use the PCR to detect the genome to identify the food authenticity. But if there has a food, the same kind of food, but grown in different culture, you use the PCR is not efficiency and it's not work, right? So they need to use another way. So if the agricultural material is affected by the environment, the metabolites will change. So we use the MS technique to do the metabolomics to identify the food authenticity. Okay. So why they point out the foodomics? That's because they want to find food fingerprint. What is a fingerprint? Just like everyone has a biological fingerprint, right? So we can identify each person by this one. But if we can find a food fingerprinting to representing a food, that's a dream of the scientific, right? So we can use this kind of compound to identify this one. So for example, we can use the oleic acid to identify the vegetable oil or not. The vegetable oil adulterated in milk or not. Okay, we can use the 1-hexanol to evaluate the drink, the oil. And also we can use the chlorogenic acid to determine there is a carrot or not. But is that true? I'm not sure. Let's think about it. If we know that the chlorogenic acid is to identify the carrot, I can buy another non-carrot material and edit the chlorogenic acid to mimic this one. So I'm not sure to detect one compound or even 10 compounds is good for food authenticity. So for food fingerprinting, they want to detect all of the compounds. So they call the food profile. So how to perform this technology? They use MS technology, okay? But is that really? MS could do that? I'm not sure. For mass spectrometry, everyone want to use MS because they imagine that, oh, MS is an amazing machine. You just put a compound here and I use MS technology, I can detect all of the compound and identify. I'm not sure. I believe that if there has a Doraemon, you know Doraemon is a comic staff, they have many of tool, right? They have a tool to point, they have a light to point this one. Okay, oh, this one is made from water or made from barrier. Wow, it's dramatic, right? But is that MS do that? No. I just mentioned that MS is used for detect the ion, physics, and chemical properties. Okay, so MS just to measure the mass to charge level. Okay, they measure the mass to charge, not molecular weight. Okay, they measure the mass. This mass is mass to charge, and then they may calculate the molecular weight. Depends on charge. If you know that the ion is 1 charge, of course the m over z is equal to the molecular weight. But the ion detected is 2 charge. Okay, so the m over z 100 is equal to molecular weight of 15. Okay, so it's not easy, right? And we can detect the isotopic pattern. If we know the isotopic pattern, we may detect the elemental composition. So we will know that how many carbon, how many nitrogen, how many oxygen in the formula. And then we do the tandem MS, called MS technology, to do the fragmentation. And use these fragments to predict the structure. After that, we have the molecular weight and also the element composition and the fragment of the structure. And then we may have the compound identification. So in this scenario, I'm not sure MS is very powerful technique for everyone. But for me, or for an expert in MS, of course, it's a very, very powerful technique. Okay. So I need to pay more attention to this, describe the MS technology for you. I know that this course is very easy course. Okay. I will make this course more easy. So just discuss. Why I want to introduce the MS machine to you? That's because I just mentioned 3 types of machine I even use, right? One is TOF, another is linear chip, and another is orbit chip. So just one term MS, they can be different machine. In addition, the same machine, for example, the orbit chip, they have different operating mode, so they can generate different data. So for everyone, MS is a machine. No, MS is not a single machine. It's a very complicated instrument. Okay, so this one is MS. For MS, there's 3 parts, three major parts. One is ion source, another is mass analyzer, and then is a detector. And these 3 parts is in a vacuum system. Okay, so you want to let your sample in your MS machine. You want to sample inlet. But for MS, we are not talking about a sample inlet. We're just talking about the ion source, mass analyzer, and the detector. So MS is only used to detect the ion information generated from ionization and detected by the mass analyzer. Frankly speaking, MS is an electronic weighting balance to measure the weight of the molecule, but the M over Z is not equal to the molecular weight. That's because of the charge. Okay, I just mentioned that. So let's see how MS gives us what kind of information. For general, we use the ion source because MS could not detect every molecule. They just detect the ionization phase gas ion. Okay, so not MS could detect everything. No, MS only detect the ionic gas phase ion. Okay. So sample inlet is just how the sample into the MS. Of course, we can use the LC or GC or EA or other, just like injection or infusion. It's okay, but we just can use the apple and put the apple into the MS machine. It's not possible. Okay, so the extraction is very important for this technology. But we are not talking this one today. So the key parameter is the ion source, because MS only detects the chargeability and the electronic gas phase ion. Ion are generated by inducing either a positive or negative charge in a neutral species. So they will given a proton or leave a proton. So they have a protonated molecular ion, or they will loss of a proton. Okay, so you detect the data showed is N plus hydrogen or proton positive, or N minus proton is negative. So now you know that a compound into a machine that may be a positive or negative. How could do that? It's based on the chemistry, organic chemistry, right? So this compound is easy to lose a proton or not, depends on their chemical structure. So you need to know what kind of compound you want to detect it. And you choose a property annihilation way to generating the ions. So the gas phase ion are electrostatics direct into the mass analyzer, and they were separated according to the mass to charge ratio. Again, the mass analyzer is just to detect the mass to charge ratio, not molecular weight. Okay. Finally, the detector measures the intensity of the ion signal, and then a mass spectrometry detects the abundance and the M/V of each compound present, which create a mass spectrum. A classical mass spectrum is shown this. The x-axis is M/V, mass to charge, and the y-axis is relative intensity. And 100% of the peak means the most abundant in this spectrum, called the base peak. Okay, so it's very complicated, right? It's easy. A compound, you want to detect it. First one, you need to know how to ionization that compound. After the ionization, this compound will into the mass analyzer, and the mass analyzer to detect the mass to charge, and then detect the abundance by such as EMT or other detector. Okay, so this is mass spectrometry, also called mass spectrometry. Okay, so it's very important that ionization. Ionization is a key parameters of MS because MS only detect chargeability and electronic gas phase ion. Okay, the process of transforming a neutral species into a gas phase ion with a charge called ionization. There are many ionization could be used, depends on the compound polarity. Again, the compound structure will affect the ionization efficiency. Okay, the earliest ionization is EI, electron ionization, or electron impact ionization. Okay, this one is very earlier technique by Dempster. Dempster is to build on the nuclear bomb, one of the scientists. Okay, and another is APCI. They will change the vacuum system into the atmospheric pressure system. Okay, and then we also have the FAB, MALDI, ESI, APPI, and the DESI, and the LED, and the SIMS, and many of ionization. So why we need many of ionization for MS technology? That's because we need to ionize the compound, right? So the later slide you may have, but I just mentioned that the MS technology is not an easy way to detect a compound. You need to know the compound or your target chemical structure or properties. Okay, so I will introduce very simple to you. This one is EI. So EI is the electron impact. It's an ionization which energetic electron interact with the gas phase atoms or molecules to produce ions. So the electron produced here, in general, they have a 70 electron voltage. So the electron here. And your analyte or your target compound is this one. And this one will accelerated by the DC and RF and to across the electronic ion. So this electronic ion will impact to the molecule and to loss of electron. Then this one will positive charge. Okay, so for EI, they only generated the positive charge in the vacuum system. Okay, so this is EI is the very earliest ionization technique, especially used in GC, gas chromatography. This one is CI. So why EI is not good? That's because EI will impact your structure, and your structure will fragment it. So you could not detect, you may not detect the precursor ion. Okay, you don't know what is your main structure after EI. So the chemical ionization is a soft ionization technique. Use a reagent gas molecule which ionized by EI first, and then reacted with the analyte by transforming the proton to the analyte to generate an ion. So this one, this is EI, right? The EI voltage here, and we're using the reagent gas here. In this case, we use methane to present the reagent gas. So EI to produce the reagent gas with a charge, and then this ionization charge, ionization gas will transform the proton to the molecule, to your analyte. So your analyte will with the protonated. Okay, so that's different, right? For EI, that has a molecule with loss of the electron with a positive charge, right? But for CI, the M over Z is representing for the protonated molecular ion. That's different data, right? If you have a molecule such 100, in EI, you will see M over Z 100. But in CI, you will see M over Z 101. Okay, that's different, okay. It's not good because for EI and the CI, they use in the gas phase. So of course, the gas chromatography. It's not good. That's because many of the compound will not volatiles, will not dissolve in will dissolve in water. So we like to use the liquid chromatography to do that. So we use the APCI. So we just change CI into a atmospheric pressure. So APCI produce primary ions on solvent spread using coronal discharge, and then again transfer the electron to the analyte. Okay, so in that case, your compound is here, and the solvent will ionize by coronal discharge, and this solvent with charge will transfer their protons into your analyte, and then your analyte will with the proton. Okay, so again, that has a protonated molecular weight. It's N plus H positive. Okay, so again, for APCI, they only has a positive charge. It's not equal, it's not good. Okay, if we detect the compound, the material is not dissolved in liquid, how to do that? So we use the MALDI, matrix assist laser desorption and ionization. If this compound such as macromolecule, such as protein, peptide, is not easy to dissolve in the liquid, we can use this one. MALDI use a laser energy absorption matrix. So the blue one is the matrix, and the yellow one is the analyte. So the laser induces the blue one, the matrix with a charge, and then this charge will transfer to the analyte, and this analyte will detect it by MS. So especially, you can see that the analyte will with the multiple charge, right? So multiple charge molecular ion will set into the mass analyzer to detect that. So for peptide and the protein, the M over Z is not equal to the molecular weight, right? Because they have different charge. They have 20 or 100 charge in the experiment. Okay, this is Tanaka Sensei. Tanaka Sensei won the Nobel Prize in chemistry in 2002. That's because he devised the MALDI technique. But in fact, right now, nowadays, we use the multi technology is not based on the Tanaka sensei. Okay, that's an interesting story, but I can explain that by English story. For loss of ionization, they use the gas phase or solid phase, and they all has the positive charge, right? But if our target compound is not easy to gain the proton, our target compound is easy to loss of the proton. How could do that? So the electron spray ionization could be used. For electron ionization, ESI, it will produce the ion by electron spray, okay, with a higher voltage applied to a liquid, and it create an aerosol resulting in multiple charge ion, who could be used for the polar or macromolecular. And of course, we can apply the positive charge or negative charge to ionization. So for ESI, they can have the positive charge or negative charge. That's the ideal ionization for everyone. Okay, so ESI and the multi won the Nobel Prize in 2002. Okay, so why I describe the more detail of ionization? That's because you could see that the different type of ionization will generate different data. And if you want to analyze the compounds, you need to know what kind of compound, and this compound structure or physical or chemical structure will easy to loss of proton or gain of proton. And then you choose the property ionization way to do that. Okay. After ionization, the ionized analyzer will send into the mass analyzer. So mass analyzer is the core, is the heart of the machine, of the MS machine. Okay. So for mass analyzer, they separated ion by mass to charge ratio. How to do that? That's based on the Newton motion equation, F equal to ma. So we want to measure the mass, right? So we give a force, and we detect the accelerated, so we can calculate the mass. The basic principle is F equal to ma. It's easier, right? So for mass analyzer, again, they have many types of mass analyzer. So different mass analyzer has different function. So the earliest mass analyzer is the sector. Okay, they are produced by the J.J. Thomson. And then the assisted research of the J.J. Thomson produced the magnetic sector. Okay, so magnetic sector is the first type of the mass analyzer. And then they define the time of line, aka TOF. They also produce the quadruple or untrap. And they may use the tandem MS technique, so-called triple quadruple, or quadruple and TOF, Q-TOF. And in 2000 years, the orbit trap was developed by Makarov. So again, I will briefly describe this technology. For magnetic sector use the static electronic or magnetic sector as a mass analyzer according to Lorentz force. If you remember that in maybe high school physics course, they will told a Lorentz force. It's very easier. That's because iron will affected by even the magnetic field or electronic field, right? And the higher or the bigger molecule will affect it less. And the small ion or the less charge of ion will affect it more. Okay, so the ion here will affected by the magnetic or sector or electronic field, and then into the detector. So we can differentiate the different molecular weight by this technique. So this is the equation. It doesn't matter. It just means F equal to ma. Okay, that's because the magnetic force is equal to the centripetal force. Okay, so that's one type of the MS analyzer. Another type is quadruple. Quadruple, that means they have 4 rods. Okay, it's quadruple. They have quadruple pores. So they have 4 rods. It's a mass filter. The ions were separated into quadruple based on the stability of their trajectory in oscillating electronic fields that apply to the charge, to a rod. It's very easy. Imagine that if we have a positive charge here, and these 4 rods will apply with the radio frequency. So they will have the positive here and the negative here. Okay, so the positive charge will disrupt by the positive, right? So they are attracted by the negative charge. So the ion will attracted by negative charge. But this one is radio frequency. So it's an alternating current. Okay, so next moment, this one will change to the positive, and this one is negative. So your ion will attracted by negative again, and again. So your ion will attracted here. And there has a direct current to put the ion move. So this one is the M over Z is separated by DC and RF ratio. Okay, so this one is a quadruple. Advance of quadruple is quadruple ion trap. Again, they use the DC and RF, but they trap the ion in a 3D spaces. So they trap this here, the ion here, and they release the smaller ion first. So the small ion will release and detect it. Okay, they just use a dynamic electronic field to trap the ion. Okay, that's a QIT, quadruple ion trap. And this one is TOF. TOF is very easier to understand. That's because if we want to measure the M over Z, the small M over Z will fly fast, and the large M over Z will fly slower. So we can detect the time of flight. To measure the time, so the ion will oscillate by electronic field to place a flying tube, and we detect the facility to calculate the M over Z. So it's a very easy way to detect the M over Z, right? We calculate the facility. So it's F equal to MA, right? And recently, the advanced mass analyzer is called Orbitrap. In fact, Orbitrap is very complicated. I briefly introduced the Orbitrap is to detect the frequency, the ion moving frequency. They just like the simple harmonic motion. Simple harmonic motion, SHM. And it's based on the Hooke's law, right? So to detect the frequency based on the M over Z. So the ion will inject to the Orbitrap, and they will move just like this one. In fact, they will move in 3D, right? They will this one. They has the auxiliary moving, and they have the radiant moving. After that, we will detect the imaging current by this frequency, and use the Fourier transform to transform the time domain into a frequency domain, and then to calculate the M over Z by this equation. So this is Orbitrap. Okay. So I briefly introduced different type of MS analyzer. Again, I just mentioned that MS is one term, but it means many type of machine. How to choose the MS technology? Because it's based on what you want to do. What kind of experiment, what kind of compound, what kind of data you want to do. So you choose different type of MS, okay? So nowadays we know that MS is a 3-part. They have ion source, mass analyzer, and detector. Of course, there's inlet. In this course, I just briefly introduced EI, CI, APCI, ESI. But in fact, they have many types of annihilation, such as FAB, ICP, MALDI, DESI, DART, SIMS, and so on. Okay, so that's just based on what kind of experiment you want to do. And again, the mass analyzer, I just told you the TOF, quadruple, ion trap, triple quad, orbital trap. They have another mass analyzer called ion cyclotron resourcefulness, ICR. It's just like the orbital trap. Okay, no. Orbital trap is just like the ICR. That's because ICR is development first. Okay. So MS, in fact, they are not talking about MS. They are talking about the GC, APCI, triple quad. That means your sample inlet is GC, and the annihilation weight is APCI, and the mass analyzer is triple quadruple. So it's not only a MS machine. No, for MS there may be LC, ESI, Q12. That means your inlet is LC, and annihilation is ESI, and then you use the Q12 as a mass analyzer. Okay, so for the heavy metal detector, you may use the ICP-MS. ICP-MS is use ICP as an annihilation weight, and they use the quadruple as a mass analyzer. So ICP-MS using single quad. Okay. Okay, I spent a lot of time to do this complicated technique. Is there has any question?
Professor.
Okay.
You mentioned several types of MS in here, but sometimes we read in the paper there are several terms like LC, MS plus MS, MS. And since you just separate the ion source and mass analyzer, but we read different terms based on this one. So could you please enlighten me about that? Thank you.
Okay, thank you. So thank you for your question. So your question is why the paper maybe use the LC, MS. So MS is a tandem mass technology. Sorry, just like this one, it's a tandem MS. That means they use different type or the same type of mass analyzer together. So for example, I just want to discuss in this slide. For example, this one has one quadruple here, another quadruple here, and the third quadruple here. So they use 3 quadruple for the mass analyzer. So this one is called a QQQ, triple quadruple tandem MS. So for the MS technique, they use different type of mass analyzer into a mass machine. Am I clear? So of course, the MS also could be done by Q12 in this one. This one is Q, is quadruple, and this one is 12. So they use Q12 to be a mass analyzer. Okay, so MS also could be do that to be a Q12. Of course, the OB trap, in fact, this one should be stand for Q OB trap, but OB trap is a trademark. Okay, so for OB trap, for this one has a linear ion trap here. Linear ion trap is a quadruple here, and OB trap here. So they have 3 types of mass analyzer together. So they call MS technique. Am I clear? Thank you. Thank you for your question. So we know that they have many kinds of MS technique in the world. So is there has any regulation to define? Yes. Based on the CENT, this one, sorry, 2021 CENT by Europe, they will define MS technology into unit MS and accurate ms. For unit ms, the definition is the resolution is less than 10,000. In fact, they only detect the unit ms. What mean? If there has a compound, the molecular weight is not the molecular weight of a compound is 0.456. But if you use the unit ms, you just detect 1, 2, 3. Okay. But if you use the accurate ms, the definition is resolution is more than 10,000. You can detect 1, 2, 3, 4, 5, 6, 7. So there has two different types of ms machine. Okay. For unit ms, the traditional way is to use the triple quadruple or linear untrap or untrap as a mass analyzer. So for accurate ms, they have the Q-TOF or Orbitrap as an analyzer. So I'm not sure if you just if a machine, a MS machine, only could detect 1, 2, 3. Is not good? No, it's good. That's because we have a tandem MS technique to do that. So we use the triple quadruple as a pesticide inspection in Taiwan. We could detect 380 pesticides in Taiwan. Okay, use the unit MS, so-called triple quadruple. How could do that? We based on the fragments. Okay, and the accurate MS, of course, they can do more. They can use the as the food microbiology, such as use the multi-type biotyper, could identify the bacteria species by using the accurate MS. Of course, they can use Orbitrap to detect multi-currents, such as 45 or 49 currents in Taiwan. Okay, so they have different types of MS machine used today. Okay, it's time. Okay, it's time to take a break. 10 minutes. Okay, 10 minutes. Thank you. If you have any question, you can just discuss with me. Okay.
Professor, can I add a little bit of my questions? Like you mentioned, like MS, there are 3 types of MS analyzer in one MS. Yeah. So in this part, I'm curious about, I thought the evolution of the MS analyzer, then ionization, happened because upgraded. That means the earliest one will not be used anymore. Isn't it true? Or still used until now? It depends on what kind of analysis that we want to conduct.
That's because of the duty cycle, the working time. Okay, the quadruple is very, very fast mass analyzer, and the Orbitrap is the slower mass analyzer. So when the Orbitrap do their duty, they have a lot of time for quadruple to do more. So the tribrid, so we call the tribrid. This one is tribrid, 1, 2, 3, 3 mass analyzers together, we call tribrid. So for tribrid machine, we need to calculate the time. Okay, the duty time, the working time, injection time to do the experiment, but not just put the sample in and out. No, okay. It's more complicated. For high tribrid, okay, it's easier to understand for hybrid. This one is hybrid. That's because there has a quadruple here, and here, and here. But in fact, this one, the first quadruple and the third quadruple, play the mass analyzer, but second quadruple play as a collision cell. That means a molecule will inject and analyze and selected by the quadruple 1, and then they will collision by quadruple 2. and this fragment will this ion will fragmentate it into different parts, right? And then we can detect or select by third quadrupole. That's tandem MS technology. They all have their own role. Okay. Thank you.
Yeah, maybe because my next semester or my next year will be focused on using this MS technique for my research. Maybe in the future, if I need a little question, maybe I can come to you to ask more about the fundamental technique of this MS, Professor. Thank you very much.
Is there any question from Japan? Of course. Am I clear? So far, so good. Okay. If again any question, you can interrupt me. Okay. So I just mentioned that MS is a powerful. MS stands for mass technology, mass spectrometry. Okay, it's a powerful and emerging as a tool to study food and nutrition domain. So it's very important, right? It's including the metabolomics and the proteomics. So this one is a reference paper for you if you are interested in mass spectrometry for analysis of change during food storage and processing. This review paper will let you know more. So MS-based method will provide the capability to detect various food composition, including nutrients such as amino acid, fatty acid, and additives such as colorants, aroma, preservatives, and contaminated, of course, the pesticides, pH, and so on. So furthermore, MS could monitor a variant of chemical reaction occurring during food storage and processing, such as oxidation, aging, rancid, and so on. Okay, so MS also provides capability to the food traceability and adulteration. So I will briefly introduce some cases of the application of MS in this course. So for this one is for nutrition. So if we want to detect the target, or we want to mention the nutrient we focus on, so we also can use the MS technology. In this case, they will talk about the GABA, okay, gamma amyl butyric acid, GABA. GABA is a bioactive compound. I'm not sure. GABA is a bioactive compound for some prevent some disease or to promote health. So they want to know how many GABA in the eggplant. And in this case, they use the imaging mass spectrometry. They can combine the imaging and the mass technique to do that. So they will detect the M/Z 107. Okay, 104. But we can see that this one is GABA. The molecular weight of GABA is 103. But they detect 104. Why? That's because MS technique only detect the chargeability and the annihilation gas phase, right? So in this case, the GABA will has a proton. So this one, 104, is a protonated molecular weight of GABA. So they detect the GABA by imaging, and they can detect the different region of the eggplant to show which region has more GABA present. Okay, so in this study, you can use even the UV light to increase the GABA sensitivity, and you can detect different region of the GABA by the imaging imaging mass spectrometry. Okay, so in this case, they detect the M/Z 104, and to know that this one is GABA. Of course, they use the imaging, right? So they can use the color to emphasize the level of the GABA in the inside your plant. Okay, so this one is use the MS for nutrition detect. And this one is preservative detection. So for any food additives, of course we can use the MS technology to do the target compound. Okay, so we use the unit MS, but we use the tandem MS technology, which means the QQLIT. First Q is quadruple, the second Q is a correction cell, and the third is a linear trap. So this is a tandem MS technology. So they stand for MS/MS. Okay, for this experiment, the target compound is methylparaben, is a preservative in food. Okay, the molecular weight is 152. After ionization with a negative ESI, okay, the ion will present in M over Z 151. And then we can correlation this, we can fragment this ion by correlation cell. And this one will fragment into two compounds. This one is 136, and this one is 92. Okay, so for this experiment, we're using MS technology to detect a compound by using 151 to 136 or 151 to 92. So in MS area, we call this two transition pairs. One transition pair is 151 to 92. Another transition pair is 151 to 136. Okay, so if we can identify these two pairs, we can identify the compounds. Okay, so for target compound, we need to know what fragments were generated by MS technologies. And after that, we can use the fragmentation to do the qualitative and quantitative experiment. Okay, that is perceptive. Of course, any food additive could do that. This one is more complicated. This one is my favorite experiment. That's because I don't want to do the common experiment. Everyone could do that. I want to challenge myself. So this one is for phytochemicals. And you can see that for this LCQ12 MS, they have generated many kinds of spectrum, many peaks in the chromatograms. And then we will identify for each peak by using the fragmentation. So for this experiment, the accurate mass is very important to calculate the molecular weight. Okay, so that's different, right? For previous study, they are not focused on the accurate MS. They just use the fragment to calculate the structure. But for this one, we don't know what kind of compound exists. Okay, so there's non-target. We don't know, but we can calculate each peak of the molecular weight by calculating by M over Z. So we can figure out what kind of compound exists in the plant or in the extract or in the food. Okay, it's more complicated, but it's useful. Okay. And also, MS could do the food safety issue on the microbiome identification. So if there has a food safety issue, such as food poison, we need to identify what kind of material exists. We can use the MS. And in that case, we can use the biotyper. It's very easy. You just sample in your sample and spot the sample into the matrix. So we know that they use the multi-matrix assisted desorption and ionization. So they use the multi-TOF to detect the ion. But they are not detect each peak. They detect the profile. They use the reference database, reference bacterial database to detect the protein of the bacteria. That's because different bacteria will have different profile, a different protein profile, right? So they set up a database for reference. And then they will do the experiment. And they will search this profile in the database to find out what kind of bacteria exists. In this experiment, the database is very important. That's because if there is a novel bacteria, your database is not work, right? So there, if the bacteria is very specific or very novelty, and your database has no information of this bacteria, this experiment will not work. Okay, so I just mentioned 3 types of MS technology on food. Each type of MS technology using different strategy to do their experiment. Okay, so for using the MS technology, the most important is the strategy, what you want to do, and you will choose the property analysis way to do and choose the correct method analyzer to do that. Okay, and this one is for metabolite detection. They have many bioactive compounds, right? But as we know, the bioactive compound will transform in our body, maybe transform into the gluconeolytic or sulfonation by your liver. So if we want to know the PK pharmacokinetic study of a pure compound, we can use this type of experiment to do that. So in this experiment, they are focused on the caffeine acid, 193, this one here. After the supplement, after the oral garbage to the mice, and we take the serial sample, we can find these 2 types of metabolites. How could do that? That's because this one is the metabolites, the molecular weight of metabolites, right? But we don't know what is this. But the fragment, we can use the MS technique to produce the fragment of the target compound. And this fragment has the 193. And this one, just like just similar to the one we oral garbage into the mice, right? 193. And then we can find, oh, it's a good cumulation, or this one is sulfonation. Okay, so MS also could do that to do the metabolite detection, just based on how you could perform the MS technique to do that. Okay, so this one is for pesticide detection. Pesticide detection is very important issue for food safety. So I just mentioned that in Taiwan, we have a method, we have a multiple method to detect 380 pesticides in food. In last year, we will detect 410 pesticides in food. But in the world, they have 1,000 or more than 1,500 pesticides used in the world. So if we could detect more pesticides, maybe it's good, right? So for this experiment, they detect 814 pesticides in a single way using MS technique. Okay, I will introduce my experiment later. Okay, that is 814, right? My experiment do the 900 pesticides in one way. Okay, we just too competitive with, we want to reach the 1,000 or 1,500 pesticides, all of the pesticides, but it's not easy, in fact. Okay, another interesting study is this one. This one's called MED, metabolomics to characterize dietary exposure study. For traditional way to do the total dietary study, they use the questionnaire to ask what kind of food you eat and how amount of food you eat. So you just, by your memory, to imagine that, oh, what kind of breakfast I eat before. Okay, it's not science. It's very objective, right? So there is another way to detect the exposure study by using MS technology. In this study, they just sample in your serum and detect the representing compound to predict how many and how frequency of food you ate. Okay. For example, they of course they do the preliminary data by eat strawberry, salmon, and broccoli, and then they use MS technique. They use ICR. Okay, and they have many of pigs here. After that, they will extract the information pig into this one, and they can find, okay, the strawberry you ate, the molecular weight, if you ate strawberry, there has a signal in your serum here, and then we can identify this compound by ICR again. So after this experiment, they will find that if you add more coffee, you will detect the dihydrocaffeine acid conjugate in your blood. It's very easy to know that. If you add tomato, you will find not carotenoid, okay? They will find hydroxycinnamic acid here. If you add more salmon, they will find anatherine in your blood. So they can mimic, they can use the metabolite identification to predict how many food or how frequency you ate today or even in a week. So that is MED study, very interesting study, and very powerful if we can use this study to detect all of us. We can mimic the healthy profile of everyone. Okay. Okay, let me introduce my experiment. As I mentioned that I like to focus on the authenticity of food using MS technology. That's because the environment will affect the metabolites of agricultural material. So in this case, we just talking about the Julius. Julius is a Chenopodium formosa. It's a pseudocereus in Taiwan. The phenomena is just like this. It's a red color, red color and yellow color. But there has a similar agricultural food called quinoa. Quinoa also a Chenopodium quinoa in Mexico. And the phenomenon, the appearance of the quinoa is here. Also the red one, right? After the refining, we may not identify this one and this one. Okay, and another one is Amaranthia. Of course, it's also a red one. And after refining, we cannot discriminate these three. We could not discriminate these three one, right? How could we do that? So we do the metabolomics study to do that. So after extraction, we use an MS technology to do the both non-target analysis and target analysis to do this food authenticity. So what's the difference? For target analysis, we have a target. So we just identify the target compound, and then we quantification the amount of the metabolites, and then we use the statistic tools to identify what kind of, which compound is more in, maybe in Julius or maybe in quinoa. That's an easy way, right? Another way is using the non-target analysis. For non-target analysis, that means I don't know what kind of compound exists in the food. All of the compound I want to know. So we use the, we just detect the molecular feature, and then we alignment each bench of the experiment, and we using the statistic. In this case, we use the multivariant statistic tool to analyze, such as PCA, and then we identify the compound. We also could do that. Okay, so let's see the experiment. Let's see the result. This one is using the non-target analysis, so we can do the chemical fingerprinting. So this one is fingerprinting by using LCSI OV trap. So it's very obviously that Amaranthia is very different from quinoa and Julius in positive and or negative experiment, right? But if we focus on the Julius and the quinoa, of course, they have difference here. So we could say that, oh, this one is the representing compounds in quinoa, and this one may be a representing compounds in juice. Yeah, we may say that. So we use the PCA, principal component analysis, to do that. Of course, we can gain a beautiful result. This one is PCA score plot. What is PCA? PCA is a mathematical algorithm to do the dimension reduction. So if you have 1,000 parameters for PC, they will decrease the parameters into maybe 2 parameters by combination the 1,000 of parameters. Okay, so in this one, we can see that this is Julius and this is Amaranthia. They locate in different quarters, right? Amaranthia is located in the first quarters, and the Julius is in the third quarters. That means these two are not the same. Then quinoa is here. So after the non-target analysis, I can differentiate Julius from quinoa and the amaranth. And more important, I can identify the metabolites based on the loading plot. So for the loading plot, in score plot, Julius is in the third quarter, right? So based on this result, the loading plot, we will find the third quarter metabolites and identify this metabolite is representing as a Julius. Again, the first quarter is represented to Amaranthia, and the second quarter is represented to quinoa. After that, we can identify the compound. But it's very interesting. In my experiment, of course, we found a compound for Julius. The compound is lutein. Okay. We also found the 3 type of compound for quinoa. It's a quercetin derivative. But we could not identify any compounds for Amaranthia. Why? That's because they has eliminated by database. There has less database to discuss the foodborne metabolites. Of course, today, many scientists working together to build out a metabolite database for food, but it's not enough. Okay, so if we just use non-target analysis, it's not informative. So I like to use the target analysis. But what kind of target we want to do? Everyone like bioactive components, right? So we focus on the bioactive compounds. For Julius, there are 3 types of bioactive compounds. The one is water soluble, is beta-alanines. The other one is phenolic compounds, maybe it's mild polarity. And this one is very higher polarity called saponins. They have many bioactive effects. So I just want to do, how could we identify these bioactive compounds in Julius? So a simple experiment just shown that if we just use a simple unit MS technique, in this case, we using the linear ion trap to do the experiment. We can identify 8 types of beta-cyanins in the Julius. And of course, we can find how many beta-cyanins exist in the seed or in the hull. It's very easy, right? And how could we do that? It's very complicated. It's based on the technique of MS, so-called MSN. Many MS. So in this case, this compound, the M over D is 727. So MS1 we may detect the 727, and then we do the MS, so we gain the MS2 spectrum. So this one we will find the 727 will fragment into 551 and 389. Okay, and again, I just collect this one. I just collect 551. And to do the second correction, to do the MS to get the MS3. So we found that the fragments of 389 were generated from 551. And again, I can select this ion to do correction again. So we will find many fragments, and then I pixel these fragments together. Finally, I know this compound is here. It's very dramatic, right? It's just like puzzle, okay? Just like puzzle. To rearrangement the fragment together to be a compound. Okay, it's very interesting for me, but it's hard work. So finally, we could identify 68 beta-alanines in Julius in just one single experiment by MS technology. And again, I could identify the different types of Julius using the beta-alanines. That's because beta-alanines is the pigment in Julius. So for these three one, it's a purple color here, and these two is yellow color here, and these two is orange color here. So I can discriminate it very clear by using metabolites identification. Okay, am I clear? Oh, it's very easy. Again, I can identify the phenolic compounds by the same way. Okay, so in this experiment, we identified 609 phenolic compounds in Julius. And then we can use the multivariate statistic tool to identify, to do a discriminated analysis. So for this experiment, this one is Julius. This one is quinoa, but it's red. So it's red quinoa. And this one is white quinoa. So we can find the red quinoa and the white quinoa is close, but it's very different from the Julius. So again, I can use the phenolic compounds to identify what food is Julius, what food is quinoa. Okay. Of course, we can identify the amount, but in this case, the amount of each phenolic compounds is not important. Okay, the total or the profile is more important. Okay, so we can use the phenolic compound profile to determine the geographical origin identification. Okay, so in this case, this one is Julius, and this is quinoa in PCA score plot. So we using the phenolic compounds, we can differentiate from quinoa and the Julius. And more important is Julius again, only the Julius sample, we can differentiate the Julius is grown in Taitung, the east of Taiwan, or grown in Pingtung, the southern of Taiwan. We also can identify. So that's what I mean. If we just use the PCR to detect the Julius and the quinoa, we could not understand this one. But the metabolites were affected by the environment. So I detect the metabolite. In this case, we so-called the phenolic compounds. We can identify, oh, this sample is grown in Taitung, and this is in Pingtung. But they all the Julius. Okay, so that's the food authenticity we want to do. Okay, very interesting. And the third one is the saponins. Saponins is the bitter flavor of Julius, and of course in quinoa. So we will identify each saponins in quinoa and the Julius. Finally, we identified almost 200 saponins in the samples, just like here. So you can see that the Julius, the saponin profile of Julius is very different from quinoa, right? So I can identify each peak one by one, just like this one. So I calculate the fragment, I calculate the environment composition, so I can pass all the fragments together to figure out what kind of saponin here. So to do this experiment 200 times, you can do 200 saponins in your synthesis or in your research. Okay. And more that, I use the molecular networking to know the relationship of the saponins. That's because saponins has their own backbone. So many saponins has the similar backbone. The differential is the derivative group. Okay, so we can put this compound together. So we can find, okay, this one is OA, one type of the saponin, and this one is HCD, and this one is OA, is another saponins. So we can use the machine learning to do the further experiment based on the molecular networking. So what I mean is, if I have another compound here, I put the MS information of this compound into the molecular networking. They will point out this compound is belong to OA or belong to pH or belong to HED. They can easily to identify the metabolites by machine learning. Okay, so we can identify more, almost 200 saponin in our samples. Okay. Again, we use the saponin profile to determine the geographical original identification. So again, the quinoa, Julius, and Amaranthia were differentiated by saponin profile. It's very clear. And interesting, for phenolic compounds, we just identify the Taidong and the Pingdong, right? But in this case, we can identify Taidong, Pingdong, and Hualien. That's, which means the environment will affect saponin more than phenolic compounds. So we can use the saponin profile to discriminate different geographical origin of Julius. Is that important? I'm not sure. For nowadays, customer want to buy a specific original food, right? So it's important. But I'm not sure it's important. Is it important? No? Just for size. But it is very, very important now in Taiwan. We have many registration to identify the honey, the brand, the rice, where they come from. So they need the technique to do that. So MS technique is very, not easy, is MS technique is powerful to do that, okay, but not easy. Okay, not just focus on the juries. Oops. I also do many experiments on other agricultural material. In this case, we use the non-target analysis to determine the geographical origin identification. It's very interesting, right? For previous study, when I do the experiment on the juries, I need to use the target analysis to do the geographical original identification. But in this case, the non-target analysis is good enough. So that's based on the different food, different types of the material. You may choose different strategy to do that. So in this experiment, we can discriminate the AMA barrier from China and Taiwan. And of course, we can localization the specific original, specific geographical origin. This is Miaoli, and it's Taichung and Taoyuan. So we can identify each type, each sample will come from. Okay. Of course, we can do the HCA to do that. The similar data show that these two is in. This is China. Okay, this comes from China. So the China sample is very different from Taiwan, right? And the Taiwan sample will divide into the Taoyuan 苗栗and Taichung. Okay, so it's very interesting technique to detect the geographical identification of agricultural material. This one is focused on the sorry, I'm not sure how to pronounce this. This is Shusidium. I'm not sure. It's called qianhu in Chinese medicine. It's a traditional Chinese medicine called qianhu. But this qianhu has different cultivars, so we can use the coumarin profile. In this case, we target the coumarin compound to identify the coumarin compound to discriminate the authenticity. And finally, we found interesting data. So they have two types of qianhu, right? They have the difference in the isobaric compound. It's an isomer. So for MS, they also detect the 427, okay, the same molecular weight. But after the LC chromatographic separation, we can separate it 2 peaks here. So we can identify this one is belong to this cultivar, and this one is belong to another. That the fragment just here. By using MS technology, we can identify this compound. Okay, so even a isomer, we can identify using LC, and then we can use MS data to confirm this experiment. Okay, so that's the application. This one is to focus on the quality of food. So previously, I just mentioned the food authenticity. But in this one, we focus on the quality. The sample is the black garlic. So for garlic, there has a smell odor, right? So many people does like to eat garlic because the smell. They have another way to eat garlic by aging. So in this case, we using the black garlic. It's an aging garlic. So after the aging, the smelling odor will disappear. That's because the sour compound here will disappear, or they will transform it by enzyme and transform to the non-smelling compounds. So in that case, we just focus on these compounds. But it's very interesting because many people say that garlic has a bioactive effect because the sulfur compound. So after the aging, the sulfur will disappear. So how could we maintain the optimized processes to maintain the sulfur compound? Okay, so in this experiment, we use the 0 days to 30 days, just 1 month aging for garlic. And we use high resolution mass spectrometry to detect the organosulfur compounds. So first day, the sulfur compound very, very enriched in the garlic, and that is a smelling odor. After aging, the oil soluble sulfur compound will disappear, or they will transfer into the water soluble sulfur compound here. So the water soluble compound here will increase. But after 15 days, this water soluble compound will disappear. So if we want to maintain the bioactive compounds of black garlic, maybe the 10-day is good. Okay. The more important is the contaminated. In that case, we're talking about the meta reaction product. For meta reaction product, some of the scientists will challenge these compounds as carcinogens or as food contaminated, such as harmine and non-harmine. That's because the sugar and the amino acid. When sugar provides the carboxyl group and the amino acid has the amide group, they will have the Maynard reaction, right? So it's not to prevent during food processing to produce the Maynard reaction products, but we can find a probable or the optimal process parameter to decrease this type of contamination. So for this experiment, if we aging the garlic to 30 days, the more Maynard reaction product will increase. But if we maintain in the 10 days, I just mentioned that we have the more bioactive compounds in black garlic and less Maynard reaction compound. It's good for everyone, right? But it's not for industrial. That's because in this experiment, when I finished this experiment, I told the industry, so you just need 10 days aging. The boss tell me, no, 10 days, the taste is not good. Okay, so for food industry, the taste is more important than that. Okay, so they call me, no, we need 30 days. So the next step, we need to find out what kind of aging processes, which means what temperature or how to decrease the Maynard reaction product is efficiency to produce the black garlic is more important. Okay, so that is the next step. For now, we can use the HRMS-based metabolomics to identify the quality of a food. Okay, in this case. Okay, any question? I may speak too fast. Any question? No? Okay. Let's move to the final experiment. This experiment is done by this year. I just finished this experiment and just published in Analytical Chemistry. As I just mentioned that for pesticide screening is very important for worldwide. But in Taiwan, we just detect 380 pesticides. It's not enough. And for the previous study, they detect 845 pesticides in vegetable and fruits. I just want to know how many pesticides in our tea. That's because tea is a very complex matrix in food. Okay, and for tea infusion, we ate just like me. I drink tea every day. I just want to know how many pesticides in our tea. And the most important is for 380 pesticides, they are authorized pesticides, which means they could be used legally. But the illegal pesticides are not listed in the 380 pesticides. Okay, so I want to know that. And more interesting, I can identify the unknown metabolites. What that means is after we use the pesticide in agriculture, they will transform by itself or by microbiota. Okay, so the pesticide will transform it into another metabolite, and these metabolites may be unknown. Okay, so I want to do that. So in this experiment, we propose a strategy called TIPS, traceable and integrated pesticide screening for 900 pesticides, and even unknown metabolites could be detected. So we use the catchers, of course, to extract the tea samples, and use the high-resolution mass spectrometry to detect the data. And then we can archive the data for the further retrospective analysis if we interested in some compounds later. And we can direct scan the pesticide by our strategy. by our screening strategy and confirm it. Finally, I found 100 pesticides in Taiwan tea. 100. Wow, that's impossible, right? In Taiwan, the registration is 439 pesticides in Taiwan. And I just mentioned that we have the multi-analysis for 380. And the maximum residue limited is 10 ppb. But I can find in Taiwan tea, in 98 samples, we can find 66 authorized pesticides. And maybe that is meets the legislation of MI law. Okay, so this 66, maybe it's good, maybe it's fine. Okay, but 11 of them are not approved in tea. They may approve for other agricultural material, but not in tea. So this 11 is illegal pesticide in Taiwan tea. Again, they have 32 unauthorized pesticides in Taiwan tea. 32. That means the Taiwan farming will use the illegal pesticide in our farming. And why we don't know? That's because we just detect 380 pesticides, but not 900, right? But I detect 900, so I find the 32 unauthorized pesticides. So this pesticide, which is unknown knowns. What is unknown knowns? We know this pesticide, but we don't put this pesticide into our inspection. Okay, why? Why we don't do that? That's because in Taiwan, these pesticides are not approved. So I don't detect that. Okay, that's unknown knowns. And more important, there has 2 pesticide metabolites could be identified, which is known unknowns. That means so far we don't know this one is metabolites of pesticide. But we know that the pesticide will transform into a metabolite, right? So we know that, but we don't know what kind of metabolites exist. In our system, we can find 2 pesticide metabolites in tea. So it's amazing experiment outcome. But again, I will mention that I'm not talking that I'm not talking that the tea farming is dangerous in Taiwan. No, I'm not talking that. I just mentioned that they may have some unauthorized pesticide used in tea farming. That not means the tea farming is dangerous. No, we just want to know why they use unauthorized pesticide to instead of our pesticide right now. So we want to know that. But I'm not just telling that Taiwan tea is very dangerous. No. I drink Taiwan tea every day. And I believe I drink maybe 1 liter per day. So it's fine, okay? I just want to let you know MS technology is very powerful to detect even the target metabolites or on-target, okay? Maybe this, maybe this one is the last information I just want to let you know. So for MS technology, for food analysis, even food quality, food safety, and so on, in fact, they have a principle called identification by pyridine analysis. What is a pyridine analysis? It's just like a pyridine. The basic analysis is based on the target analysis. That means you know what you want to detect. If you know that, you just use the LCMS or MSMS. It's okay. That's because you have standards. You have standards, you can use the unit MS or tandem MS to do that. It's very, very easy, okay? But if you want to do is non-target analysis, you don't know what kind of compound exists, you need accurate math. So you need such as TOEFL to do that. And you need a database to search, to match your data, to identify what kind of compound using the non-target analysis. But the most worst situation is unknown compound. Just I mentioned that for pesticide screening, they have some unknown compounds. We need higher accurate math, such as OB-CHIP or Q-TOEFL. And then we need to know how to puzzle each fragment together to be a compound identification. It's not based on the database. No, database is not work in this situation. So again, for MS this term, MS means different types of MS machine. And the same machine do the different types of work. So if you want to do this kind of experiment, you need to know what kind of compounds or what kind of experiment you want to do. And then you have a strategy to do your experiment. So MS is not just the ELISA reader. For ELISA reader, you just put your plate and push your button. They will read out the data, right? For MS, it's not. It's very complicated, but it's very, very powerful and very, very advanced in this world. So you can do that. Okay? I'm sorry, I may finish this course today. So thank you for your listening. Thank you. I will appreciate any feedback. And if I could explain more detail. Okay. Any question? Thank you. So, am I clear? Any question from Japan? No? Okay. If you have any question, I leave my email address here. You can set your question individual, okay? Or maybe we dismiss. Okay. Thank you.